would be for me to go over some very high-level material about like why do we do optimization anyway, right? It's actually fun just every now and then, even if you've been doing it for a while, to go back to the very beginning and think like, why do we do this? And I have a couple of examples I'll show and things like that. But and then maybe I'll even finish early and have questions and stuff like that. So the first thing is just to go back to the basics. Everyone here knows what an optimization problem is, right? So I'll go pretty quickly, but I want to get to the parts where you've asked, like, what do you do with this, right? So, I mean, the point is you have some variable. I guess when you're describing the generic one, it's a variable, not multiple variables with different names, but that you want to choose, right? And I mean, a good name for this from OR is actually a decision variable, which is just a beautiful, because it's exactly what you have to decide. And you can be judged two ways. First, there are going to be the hard constraints, these, and anything that violates them at all is just deemed unacceptable. And then there's a soft constraint, or a soft objective, I would say, which is the main objective, and it's sort of a best effort thing. You'll take any number there, but the smaller it is, the happier you are. So that's what that. And of course, really in real problems, you have multiple objectives, as we saw a talk on. You have multiple objectives, and maybe you're not as you might have a soft-ish constraint, like you'd like this to be less than 3, but would it kill you if it went over 3? If something else good happened, you'd be fine with that and stuff like that. But this is sort of the extreme version of it. Okay. Okay, so now we're just going to talk about like just broad classes of areas where you use optimization, right? So the most literal reading is that you're going to find good actions, right? So X is something that actually happens, like you decide a trade list and it gets executed, right? Or you decide the airplane control surface deflections for the next 10th of a second, right? Or the thrusts and maybe the main engine thrust angle on a rocket for the next 10th of a second, right? So these are things that like really happen. Be a scheduler sign, a resource allocation. You allocate resources for the next, whatever, 10 seconds to the data center or something like that. Okay, so and the idea is here, let's hope. Okay. So here, the constraints limit what you can do, right? And they also impose conditions on outcomes, right? So that would be the idea. And the objective is just something that makes you happy. Like it could be the total cost of doing something, or the negative profit. It could be the deviation from a desired or targeted outcome. It could be risk. It could be fuel use. These types of things. So these are this is the most literal reading of what you'd use optimization for. Another huge area is X doesn't represent an action. There are parameters in a model. And it could be a statistical model, it could be a prediction model, it could be all sorts of things. This is actually getting we'll see. So here, the constraints would impose the limits on what if you're estimating intensities, they have to be non-negative, for example, or covariance matrix has to be positive semi-definite at least. The objective is, typically a sum of two terms, right? A prediction error, which is you want your model to fit well on some historical or training data. You also want the model to be not that sensitive, so that when you actually field it next week, it's actually more likely to work, and that's a regularization point, right? So, and I like to say, but normally I like to say if my statistician plan, it won't work as well on Maris, but if like Trevor Hasty or Rod Fitzgerald were here, I would say that's pretty much all of statistics, and much of AI and blah 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 and all sorts of other things. But anyway, okay, but they're not here, so I won't say that. Okay. Oh, we are? Good. Okay. What's that? Since I said, I don't know. I may have. Who knows? We will find out, right? You can actually spoil it. But that's okay. Okay. Perfect. Okay. Let's see, but this will be Okay, I'm not getting a super good. Okay. So yeah, this is finding good models. Okay, well, hopefully this will work. Okay, yeah. So this is one broad class. Another one is worst case analysis. This is actually super interesting. That's the USB to. Yeah, let's try this, and if we'll see if it's the same talk too. It'll be fun. So another huge area is worst case analysis, right? So how do people really do worst case analysis? They generate stuff randomly, or they'll generate things at the corners of some boxes where they believe parameters lie, and that's just good engineering. People do that. You can also do stuff where highly directed, where you would actually have an optimization problem, attempt to find the worst case, right? And then what you do is, if you look at the worst case, it's like kind of confronting your worst nightmare. In fact, one name for this is the nightmare machine. I remember. So, but the basic idea is you look at it, and then you look at it, and if it's bad but not terrible, you would say, well, okay, now I know the worst thing that could happen is something like that, right? Usually, by the way, it is terrible. And then you go back to the constraints which describe what you believe your adversary is capable of. And then you look at it and you go, no, that would never happen. Then you tighten it and everything, that kind of stuff. But anyway, so this is a good area. It is used sometimes for this. Okay. So let's see. It's not quite the same. It's okay. It's fine. Whatever this is. Okay. So, I mean, another huge area, and this is one that people should think about. I mean, these are obvious things, but it's good to point it out explicitly every now and then, is optimization-based modeling. So here, you model an entity as taking actions that solve an optimization problem, even though it's actually most interesting cases where that is false. Okay? So that's the model. So this would be like your rational actor in economics or something like that, or an organism that say is going to act to maximize its reproductive success, or they do this in biology in flux space analysis, where you have a cell, you track maybe a couple of hundred metabolites, 1,000 reactions, you have upper and lower limits on the reaction rates. One reaction is very important. It's the reaction with the cell growth. Then you literally solve an LP to maximize the cell growth, right? If that's below a certain number, you predict it's going to die. If it's above a number, you think it's going to live and thrive. Okay? So you literally solve an LP. Here's the shocking part. It has stunning predictability, right? So it's kind of cool, right? So and a friend of mine does this because here's what he does. They'll say, like, to check that you have to validate it, right? They'll say, go knock out these 4 genes, which would take out set a bunch of the maximum reaction rates to 0. I said, how do you do that? He goes, oh, I just sent an email to my postdocs. It's done the next morning. Okay, so that's how they do that. And then you find out, like, did it live or die? Anyway, these make it like quite, and it's kind of interesting because, I mean, if you're trained, kind of like mathematically, you're going to have some personal, it's going to be hard for you to do this, to basically commit such hideous, egregious modeling errors, right? Because we know that a cell does not solve a linear program before it decides whether it should thrive or die, right? So, however, these things, they often work really well. So I mentioned this just because the whole entire field's based on it. Like, for example, Western economics, they kind of agree with it. I have friends, and I run them by, and they go, yeah, that's kind of what we do. So anyway, okay. So let's go to the basic use model. So basically, you're moving from you're moving from something where you say what to do in a situation or a context. You're moving to something where instead you articulate what you want, and then you let an algorithm decide what. Right? So that's. I mean, I know this is super obvious and super basic and all that. This is the root of all sorts. I've had lots of conversations, like a while ago, I had conversations with older colleagues and things like that about using, let's say, MPC, how to use optimization for whatever it was. We were talking specifically about flying an airplane, and he's like, I don't get it. He said, look, if the airplane is like tilting like this, you raise your right aileron and lower your left one, and it puts a torque on it, and it steadies it to level up. Like, yeah. He goes, what do you do? And I go, oh, well, we have a model, of how what you do affects the airplane, number one. Oh, and then we also say we like to fly level. And he's like looking at me like, these people are impossible. And then he said, but what would it do in that situation? I said, it would raise the right aileron and lower the left one. Like, and he's like, this seems too gay. He never was convinced, by the way, but it doesn't matter. He was wrong. So anyway, but that was the basic. That was actually the basic. It was about this very. I have a neighbor. She's in a business school. We were chatting about this, and she asked like, "What do I do?" So I said a little bit at a very high level. Like I talked about this kind of stuff. And she looked at me and she said, "That's exactly what we teach in the business school." I was like, "What are you talking about?" And she said, "You teach like convex." No. Here, what we do, we say it's very important. Here's what you should learn. You should learn to specify the metrics, and then you let your people or that division go execute it. Hopefully without landing in jail. Okay, so so it's like, okay, well, at that level, I'll accept that as an analogy. So it was anyway. So the point is, these are hardly novel ideas, right? I mean, kind of obvious. Okay, then we get to the main question: is can you solve it, right? And the answer is generally no, you can't, right? But the counter answer is you can. People try to solve. You try to solve an approximation, and it often doesn't matter because, in fact, most optimization problems are only surrogates for what you really want. So here's what you really want is a model that makes good predictions tomorrow and in the future, right? What you actually, as a surrogate to achieve that goal, what you do is you minimize something involving how it would have worked on historical data, plus a term that regularizes it for being simple. Okay, so that's not what you get paid for, right? So in whatever that's what if you're doing finance, you're not paid for solving a Markowitz, right? You're paid for making money, for your clients or whatever, something like this. And the Markowitz thing is merely a surrogate to kind of figure out what you want. So, okay. And, it doesn't, and sometimes it doesn't matter, right? I don't see people who train deep neural networks. By the way, unless they train to zero, in which case it is the global optimum if the loss is non-negative. But turns out that's not even the whole point. They're not racked with, questions about, oh my God, did someone else do better than this or something? What came out was a beautiful LLM and they're happy with that. So, okay, there is a huge exception. It's just convex optimization, right? So, and you all know this. There are people who are radical on this, and they actually say literally anything that's tractable, anything in applied mathematics is tractable. Goes back to convex optimization. I think that's a bit radical, but there are people who say, and I'd say, like, come on, dude, like, are you like eigenvalues? I can maximize, x transpose x subject to, x transpose ax is less than 1 or something. He goes, yeah, that's because the dual of that, it's non-convex problem. The dual of that is SDP, and there's zero duality gap. So anyway, so these are people you can't whatever they say, they're going to come back with something like that. That seems a little bit too complicated to me. No, it is true that every algorithm in your undergrad CS course that's polynomial prime, every single one, the LP relaxation has zero duality. So you could have solved it by LP. By the way, then you ask, should I solve, the shortest path using LP? And the answer is no. The algorithms that you learned in that CS class were way faster. So, but it's a true statement that those are solvable, right? So, okay. So say a little bit about it. Everyone here knows about it, but actually the cool part about it is absolutely nothing more than a statement about curvature. It's the objective has to have non-negative curvature. Inequality constraints have to have non-negative curvature, and the equality constraints have to have zero curvature. So it's nothing, and it's weird because if you think careful about it, it's asymmetric. This doesn't make any sense at all, right? Like you would guess, a normal person would guess the following: if I said, I have an algorithm, I can solve these problems perfectly, but now the objective is like concave. You'd think you say, give me your algorithm, and you just find something where you're doing a step, you flip the sign on the step, right? I mean, this seems like that, right? That seems reasonable, and that should work, right? And it doesn't. So it's kind of, once you play with this stuff, you kind of get all this, but it's very weird. Think about it. There's this weird asymmetry to it, right? Which is cool and fun. Okay. Okay, so then there's the question of, when is the optimization problem, easy or hard? And the classical view is the world divides into like linear stuff, like linear programming, and then the other was like, ready for this, non-linear programming. That's spooky and hard, and then integer programming is hard, whatever, something like that. So that's the so that classical view, it turns out, is just completely wrong. Basically, the convex, more or less. That's it. And there's a great quote. I've helped propagate it. It's from Harry Rockefeller. And it's something like, the great divide in optimization isn't between linear and nonlinear, it's between convex and non-convex, right? So actually, I just had lunch with Harry Rockefeller a couple months ago. He's doing great. And I knew this anyway. That quote is taken completely out of context. It is not what he meant. Okay. But he said, but I keep hearing secondarily from you going places and telling people, and then they come back to me and say, that's a great quote. And then he said, but I decided I like what you imply I said just as well. So he's totally okay with it. He's fine with it. Okay. Okay. So how do you solve them? Well, I mean, again, I think people here know a lot about this. Small problems, you can use integer point methods, and you can use first order methods for larger ones. And actually, a super important point, they don't require an initial pointer babysitting or tuning. That's actually unbelievably important, right? Because that's actually the real advantage. This was explained to me by a hardcore circuit designer, who once told me, I said, he said, what? So what? I mean, I said, yeah, but this is like the global optimum. He says, it's not the global optimum. I was like, well, it is. It's weird for me to say that, but this is the global optimum. He goes, no, you could have used a different circuit topology. I'm like, yeah, that's true. Okay, if that's open, then yeah, it's not the global optimum. And he said, here, I'll tell you why this is useful. He said, this is useful because these other methods require us to come up with a pretty good design, and then these optimization methods will then polish it. They'll take a good design and they'll make it, very good. He said, this is good because there's no babysitting and you don't need an initial design. He said, that's the real practical advantage. I thought about it, and I walked out of it, what an idiot. And I thought about it for like a year or so, and then I decided he was right. So anyway, that's it. So, I mean, the other thing is you can embed them, right? Once you get over a certain level of reliability, you can embed it in the control system. It can be making 100, it can be making, if something's advisory, we don't care. Like that's not a big deal. It's telling you a schedule and admits a schedule and it doesn't look right, you can say no or something. The supply chain, if it's only emitting a suggestion once an hour, a person can look at it and overrule it, right? But you can also put in a control system where it runs 100 times a second or 1,000, right? Which is really cool. That's what Max did and then didn't talk about. Code generation. Okay. Okay. So the approach, what's the general approach to all this? The general approach is you take your practical problem, right? And this is kind of loose, right? There's some questions about, how to formulate it. And what you do is you try to formulate it, your problem is convex. And then the idea is if you succeed, I mean, then, as a first cut, you can basically say, it's solved, done, that's it. It's just done. I know how to do that now. Right? So, I mean, of course, if it's like, real time or something like that, or gigantic scale, obviously in those cases, you might have to go and do a little bit more, but generally speaking, you're just done at that point. Okay. Now, there are some, when I'm teaching the class right now, so we teach this, and then during the class, you're in a little sandbox where everything is convex or whatever, and if it's not, we warn them, we put up those slippery floor things around where, where we're going, we warn them, we get trigger warning, everything. So, fine. But the way it really works is you're going to learn some of these tricks, right? And the tricks would be things like change of variable, right? That's one. You can approximate the true objective and constraints exactly as the way you saw Max just talk about it. Right? So that's a great street fighting trick. Somebody comes and says, make me the minimum fuel trajectory. And you go, great, how does fuel use go with? And they give you like something this thick with all sorts of like physics, TDE, wind tunnel, all sorts of crazy stuff. And you're like, oh my God. And usually the best thing there, say you have a simulator, you have some data, generate yourself 1 million points, and then go hit install Max's thing and transmitting, right? Okay, then relaxation, which people, it's a very wide range of, so what everyone here knows what it really is, and we don't tell people this in public. Here's what it is. You simply ignore terms or constraints that you can't handle. Now, how you could take an idea that simple and make it sound so unbelievably complicated and sophisticated. What are you doing? Oh, this is a Lagrangian. I'm using some of where, and it's like, come on, it's like this is really what it is, basically, right? Don't make fun of it. It's like making fun of those models of an entity where it's based on optimization, right? These things have a very good track record, various relaxation, right? And in fact, in many specific cases, someone says, I want to solve that problem. And you go, I can't. So I'm going to do this relaxation. I'll solve a problem that's kind of close to what you want, and here it is, right? Then later, somebody will come along and figure out, actually, that first problem was stupid anyway. You didn't want to solve that. You really wanted to solve the relaxation. Very good example is risk and Terry Rockefeller's, CVAR, conditional value risk, right? So everyone uses VAR because everything is expressed in that. All these banking laws and things, they're all based. It turns out it's not a coherent risk measure. Basically, it doesn't make any sense. Sorry, you're learning that for the first time. What's that? Yeah. Yeah, sure. But the point is that when they mess up, the world economy doesn't go down, right? So that I think that's, yeah, you got a point there, right? So, but okay. So, all right. So no one's upset now that you know that like Basel, whatever these things are just based on a non-coherent risk measure. Okay, that's fine. That's cool. Fine. Okay. So modeling language. I mean, obviously we're kind of here for CVXPY. And you know all this kind of stuff, but it's really kind of because I remember the world before I was teaching this class before we had these things, and it was fun. I mean, you can teach the theory, that doesn't help it. I mean, it doesn't hurt. It's the same, right? But then when you actually want to do a numerical example, which is in fact what the whole class is about, is actually this stuff is actionable. Like you can actually do it. It's a pain in the ass because they have it would be maybe an LP, and you had to make your own little symbol table and say, well, I really have three variables, X, Y, and Z. I'll stack them X, Y, and then you're doing your own index arithmetic. I mean, it's ridiculous, right? Like we have a derogatory name for that. If you do that yourself, it's called matrix stuffing. So if you have friends, or another phrase is friends don't let friends do matrix stuffing, right? You take them aside and you say, dude, what are you doing? And they go, well, I just found this solver online. It minimizes C transpose X subject to AX, blah, 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 less being too bound. Okay. Then you say, what are you doing? And you go, well, in my variable, I have like 4 different things and I had to stack them. And this was a matrix, but now it's stacked and blah, blah, blah. And you're like, what are you doing? Anyway, so there are still no one here, but there are people who still do that. And what I'm saying is by the way, if you see that happening, even if you don't know the people, you step up and you let them know. As a good Samaritan, you just step over and say, I'm sorry, what are you doing here? And it's like, oh, I'm getting ready to call C-Flex or something. You're like, stop right there, just stop, just go back and do something fine. So, but to me, the coolest part about the development of these things is it gets back to this basic idea like that I talked about with my business school neighbor. Don't say how to do something. You articulate what you want and then let an algorithm do it. I mean, I guess in this case, let your subordinates do it, in her case, right? But in this case, in this context, it's let the algorithm do it. And this gets really close to it. So the whole point is you write down the CVXPY stuff. Also, I should tell you some fun stories about this. I used to do a lot of convex optimization control. So I'd go to a control conference and I would say, okay, here's a control problem, blah, blah, blah. I'd say there, now it's a convex problem. I'd say, do I solve it? I'd solve it. And then people would say, how'd you solve it? You use Nesterov method, you use this, blah, blah. And I'd actually look at them and say, it's none of your business. Absolutely not one. Doesn't make any, I'm not going to tell you. It's none of your business. And they're like, and they'd say I'd say, look, I know 50 ways to solve that problem. I used one of them, okay? And they would all get the same answer or whatever if it's a unique solution, right? So that's not the point of this. The point of this is it's convex. But academics, they want to zoom in and talk about the details and they get all excited about, Nesterov acceleration and blah, blah, blah. And that's important, but I don't think it should be public, right? This should be how people use optimization, right? I mean, most. Okay, there's a bunch of implementations. I don't know if anyone said it yet, but it turns out like one of the very first of these, I mean, there's obviously been domain-specific language for optimization, like AMPL and GAM. Those have existed for a long time. But for one specifically that support convex optimization, the first one is this one. It's by it's something called YAML, a very obscure reference. It's yet another LMI preprocessor, which is a weird reference to many other computer science things from the early 80s, like YAC. You know what that is. Okay. Okay. So I'll look at some examples, and you've seen plenty, but it's just sort of fun, and then I'll conclude and we can chat about stuff. So here's Markowitz optimization. This is where you're constructing a portfolio, and you're going to decide what you have some. You're going to work with the weights. That's the fraction of your portfolio wealth you put in each of a bunch of assets, right? So, and this is from like 1952, and actually was a stunning advance because before that, it was kind of cool. It was like people said, "How do you construct a portfolio?" And they'd say, "Well, you should definitely have more than 10 assets. That's a good idea." And they said, "But we'd recommend less than 30." And you go, oh, "Okay, thanks." And you go, and don't put them all like in pharmaceuticals in Switzerland. And you're like, "Okay, thanks for the advice," right? And it was just like that was literally what people thought it was, until essentially a PhD student, Markowitz, said, "How about if we make it an optimization problem?" And it turned into a quadratic program, that was just coming online. And in fact, go back and read the original papers on quadratic programming. They cite this new idea that you could construct a portfolio as one of the applications, right? So it's very, very cool. So, okay. So you solve a problem that looks like this. This one just happens to have an analytical solution, which is silly. But the idea is you literally write down what you want. In fact, I wouldn't even bother me unless you're in some speed issue or something, right? Then this is perfectly good way to do it. So at least it's a good unit test when you write your NumPy to make sure it's doing the right thing. So, okay. But it turns out, and this is the point of convex optimization, is that it is accretive, right? I can add other stuff to it incrementally until I get what I want, right? And it turns out it doesn't take much. So I should preface this by saying basically since about 1960 when people started using Mark, and I should say that is what is used. But, however, there's an entire academic sub-discipline, which and the title of it is Markowitz doesn't work. I couldn't make this up. This is a true, and then all of them start. I mean, there's one being published like right now, and here's what it says. It says, and this is like for someone versed in engineering, it's like laughable. It would say something like this. It would say, "Yeah, if you pass in the wrong data to your problem, you won't like the answer." And you're like, "Oh, okay, right." The answer to that is then don't pass in the wrong data, right? And so people do things like they find an empirical covariance matrix and an empirical return, and they plug it in. They go, "That's a terrible portfolio. Look, it doesn't work." Anyway, so it works. You just have to know what you're doing. So okay, so you just add a couple of things, and you end up with something that's kind of like like something that the payload is around 4 lines, I would say, right? This thing right here, that's completely practical. That's a 4 line. Okay, I might go with 10, but this would be enough to actually do real trading right there. So this is kind of cool, right? And the best part about it is, if you get some other weird thing, if Nara says don't do X, Y, or Z, has another constraint, as long as it's convex, I just type it in. So it's very cool, I think. Okay. Cool. Let's look at our second example. Second example is in just residential energy management. It's very, very simple, but here's the idea: is we're gonna look at this like we'll optimize over a day or two or something like that. And here's what we're gonna have: 15-minute intervals. I'll tell you how much solar is available. You don't have to take it all, right? You should, right? Because otherwise you're leaving joules on the ground, right? But if you don't have a place to put it, like a load or a battery is full, then you're gonna have to curtail, right? So you have this coming in. You can get stuff from a utility, and we'll say that the only thing you can do is pull power from the utility, not push it back in, which more or less matches what's called NEM free. So the lobbyists basically arranged for no one to be able to sell anything back to them. So, they pulled a good one off. Actually. So okay, so you're going to choose ST to solar power. That's going to be less than what's available, and almost always, right? Because that's why you paid for those panels. They're amortizing up there, not using the full power that's coming off from the so you have a battery, and you can charge and discharge the battery, and there's maximum limits on that. And you can get this is the problem in one page, but you could get it would take very little to make something very practical. But as a matter of fact, I think all of Tesla's grid scale energy products, cargo container filled with batteries, the Raspberry Pi, and actually at least a few years ago, they were all running CVXPY. So it's kind of yeah. So okay. So sorry, I'll look at a quick example. It's just a quick example where here's some solar availability. That's obviously the night. This is load, and I kind of these are actually all real. They might not even be at the same house in the same place, but still they're real, whatever they are. That's not the point. And the prices are real. These are actually like mine or something at home. So that's peak, that's called shoulder, and that's I forget what that's off piece or something. Looks something or it looks like this. Actually, this is not quite well. Close enough, right? Okay. So then and look, everyone here, what you want to do, right? What you want to, let's see, if you have excess power from the solar things, you want to pump it into your battery. So you don't want to arrive at the beginning of a super sunny day with your battery full. We all know that, because then your joules will come in, and you won't have anywhere to put them. You'll have to spill them over the edge, lose them, right? So and you don't want to drain your battery right before the prices go through the roof, and then someone turns on the heat or something like that, and now you're paying maximum prices. So we all kind of know what to do. It's kind of obvious, but just write down 3 lines or something like that, and it just kind of does it. I won't go into the details, but it's kind of cool. By the way, this idea that you can write 3 to 5 lines or something, maybe go up to 10, if you include plotting and things like that, and look at different. Super fun for people. Just get a class with people from 35 different departments, and I love the idea that somebody in a PhD student in statistics has to now design a circuit. I don't know why that appeals to me so much, but it's really cool, and they do it. They have to. It's a course requirement, right? So, but that's okay, because I have circuit designers who then fit Cox models. So I think it's all fine. Okay. I won't go into the details, but it, for things this simple, it usually does something that's very close to what you would think. If I put a network in there and I put lots of other stuff in there, it wouldn't be a problem, and you could do a lot. This would still do that. Okay, so I'm just going to get to some conclusions. And so, you all know this, but they're just weird. It's a weird subclass of optimization problems characterized only by extremely simple curvature requirements, which is kind of weird and asymmetric and counterintuitive. They come up in a lot of applications. They can be solved effectively. And of course, the whole point is it's easy to specify using DSL, right? So what that means is it's actionable. This is something you can actually do this, right? This is not something where you learn about something. Oh, it's so interesting. Thank you. I just got a lot of insight. That's really good. This is no, you can code it in 5 minutes kind of thing, right? So that's good. I didn't talk about it, but you can, because of their reliability, not maybe all the things you would use, but they can be made to have, they can be custom made to have a reliability of 1.0. Okay? It's maybe not the ones you're using, it's maybe not the default solvers and things like that. You can have a failure rate of probably 1 minus 4, something roughly. Okay? But you can arrange for the solvers to have reliability 1.0. They will work, period. They will not fail. They may fail to find a super accurate solution, but they'll be close enough that for your application, everything's going to work just fine. Right? So, and that means you can put them in embedded systems, right? So, which I think is cool, or guess the best way to think about it is one less thing you have to worry about. So it's cool. Okay, so I'm gonna quit here, but I'm perfectly happy to answer any questions anybody might have.